So 4.3 is called How Derivatives Affect a Graph. I kind of renamed this to Connections Between Graphs and Derivatives. So now we're going to dig a little bit deeper and talk about derivatives and what that means for different parts of a graph. And that's going to allow us to be able to draw graphs eventually really well with the curvature taken into account. So just a note that 4.2, we're going to come back to that. We're skipping it for now, so we're really just picking up where we left off in 4.1. So let's take a look at example 1. It says find the open intervals on which f of x equals x squared is increasing or decreasing. So this is something that you're going to be asked to do in this section, and we're doing a simple example here because you probably already know the answer and want to connect with your intuition. So here's a graph of y equals x squared, and we can note that the graph is decreasing from negative infinity to zero because we have a negative slope of the tangent line for all the tangent lines that would be coming in to x equals 0 from the left. So, or it's negative slope all the way. Then the graph is increasing from 0 to infinity because we have a positive slope for all the tangent lines on that interval. So another thing to note is we talked about critical values, and the critical values of y equals x squared, the way we'd figure that out is we take the derivative and we get 2x, and then we want to see where the graph for which x that the y prime equals 0 or it does not exist. So 2x doesn't not exist or exist everywhere. No problems there, but we do have the derivative equal to 0 at x equals 0. And so that's a critical value. Another thing to note is that the derivative 2x for x that are negative, or in other words, on the interval negative infinity to 0, that y prime is negative, which indicates that the slope of the tangent line is negative. So I'm just trying to develop all these connections here on different ways we can think about increasing, decreasing. So we could also talk about y prime being equal to 2x is positive when x is positive, and so therefore it's increasing on the interval 0 to infinity. And we have a critical value at x equals 0. So that's not included on our intervals of increasing or decreasing because the sign of the derivative is just 0, it does not have sign. Is another way to think about that, or it does not exist would be the other case that we don't have in this problem. So one thing that we're going to be doing is we're going to be finding the critical values, and then we're going to break up intervals that are having the borders with the critical values, written from left to right, so pretty simple one in this case since we only have one critical value. And then what we figured out so far is we went from decreasing to increasing. Eventually we're going to do this based on the sign of the derivative because we won't have the graph. And the character of the increasing, decreasingness of the graph is going to be the same on that entire interval because, again, we're looking at the derivative where it does not exist and where it equals 0 is going to be a potential transition between increasing, decreasing. So we'll talk more about that later. The point I want to make right now is that when we go from, in this example, decreasing to increasing, and we have a critical value between there, then we have to have a minimum value here. It might not be an absolute minimum, but certainly it's a relative minimum, because that's the only way that we can have a function go increasing and decreasing. It's got to be a low point. So just showing another scenario, not for this example, if we had on the interval negative infinity to 0 an increasing function, and then we had a critical value at say x equals 0, and then from 0 to infinity it was decreasing, then note that that would that have to be a max, min, or neither? So the reason I made these arrows in this way is you can kind of see it's a simplified form of the graph in a way. So notice we're going up the mountain and then down. So what we have here is some sort of maximum. Now again, it might not be absolute maximum, but it's certainly going to be a relative max. So now, hopefully that all that stuff made sense and matched with your intuition or the things that you already know, and just making some connections. Here is some of the actual justification for doing kind of what we were doing above, and then also talking about some of the gray areas. So the increasing decreasing test right from your book says if f prime of x is greater than 0, in other words the derivative is greater than 0, or it's positive, slope of the tangent line, a lot of ways to describe that, on an open interval, then f is increasing on that interval. And we observe that, that makes sense. If f prime of x is less than 0, or the derivative is negative, or the slope of the tangent line is negative, on an open interval, then f is decreasing on that interval. Also, we have the first derivative test. Suppose that c is a critical value of a continuous function f. If f changes from positive, so f is increasing, to the derivative being negative, in other words f is decreasing at x equals c, then f has to have a local max at x equals c. So this was the last case I went over where it's going positive, negative slope, it's got to be like a little mountain peak there. Maybe not the summit, but you know, it's a local high. It's got to be. If f prime changes from negative, f decreasing, to positive, f increasing at x equals c, then f has a local min at x equals c. And we talked about that case as well. So here's a third case that I didn't highlight up above. If f prime does not change sign at x equals c, so in other words, if we had a critical value and we were looking at those intervals and we got f prime positive and then the next interval was f prime positive again, that's one scenario. Or f prime is negative, goes to f prime negative on the next interval, and the border between those is the x equals c, which is a critical value. It says here then f has no local max or min at x equals c. So we're not always guaranteed a min or max at a critical value, and that's something we went over in 4.1. An example of that, just to kind of show you a picture here, is a classic example of this would be y equals x cubed. So notice we know the graph of this. We're going to move towards not knowing the graph and creating it, but just kind of seeing how these mechanics are going to fit up with the graph that we already know. If you take the derivative of x cubed, you get 3x squared. When you set that equal to 0, you get the critical value of x equals 0 again. There's no other place where we have a critical value, so because there's no other y prime does not exist thing going on here. So anyway, we have these intervals here that were the same as x squared. The sign of 3x squared is a little different here. That's our derivative. Notice when you plug in negative x's, which would characterize this whole interval from negative infinity to 0, you're always going to get a positive number because we have the x here being squared first and then multiplied by a positive number. So that's kind of a little bit different thing than the x squared case, y equals x squared. Here, for plugging in positive x, we get a positive x out for y prime, or positive value out for y prime, I should say. So notice we go from increasing critical value to increasing. And that's exactly what the graph is showing, right? So we have an increasing function, kind of takes a break here at x equals 0. There's actually a horizontal tangent line here. I didn't kind of draw that really super good. Maybe I should kind of accentuate that a little bit. It's kind of a little bit more of a transition like that. Looks a little bit better. So there is a horizontal tangent line, but then it goes, oh, actually I'm going to keep increasing. So we have no local max or min at x equals 0, which is a critical value for the graph of y equals x cubed. And so that is explaining that third case. Let's do an example. Find the following for the function f of x equals x cubed times quantity x minus 2 squared on the interval -1 to 3. So the following are intervals of increasing and decreasing. local max and mins, if any, absolute max and mins, if any. So we're basically going to go through all the things we need in those tests, which again we're up here, increasing, decreasing test, first derivative test. Okay. So the first step, I guess we're working on A, but we're going to need this later on stuff, so that it kind of builds to everything we need, is we need to find the critical values. Those are the borders for the intervals on which we're going to test for increasing, decreasing. Alright, so I'm just going to go ahead and do the derivative of this with the product rule. So I have my x cubed. I need to take the derivative of x minus 2, that quantity squared. I'm going to use the chain rule. So I'm going to drop down the 2. Original stuff on the inside is x minus 2. New power is 1, which I'm not going to write in. So that's the derivative of the outside function evaluated at the inner function g of x. And then multiply by the derivative of the inner function, x, its derivative of x minus 2, which is 1, so actually didn't do anything this time. Then we have plus rg, which is x minus 2, that quantity squared, f prime, or the derivative of x cubed, is 3x squared. So there we go. So notice we don't have, I like to do the f prime of x d&e thing first because it's easy to forget about it. It doesn't happen too often. So I like to actually take care of that first, or kind of at least think about it. What we got here, we could distribute and stuff, but we got some powers that are integers, and no negative exponents possible, where we'd have division by 0. What we got here is polynomial, so we're not going to get any critical values from f prime of x. Does not exist. So then now we are going to move on, and the only possibility for any remaining critical values is where f prime equals 0. So let's start working on that. Not a whole lot to simplify here. I'm just going to write the 2, and we want to look at this closely before you start launching into distributing and stuff like that. I'm just going to kind of write it in a way that's a little bit easier on the eyes. So now looking at this and keeping in mind that we're trying to find the x for which this whole thing is equal to 0, notice kind of the crafty thing about having used the product rule for this derivative is I have something that's already partially factored with an x minus 2. And also we have an x squared factor. So the GCF here, I'll write it over here. The greatest common factor is from the x cubed, x squared stuff is going to be x squared. And then we also have a factor of x minus 2. So let's look at that. X squared times x minus 2, factor it out. What remains behind is a 2x for the first part, and then over here we have a plus 3, and then 1x minus 2 left over. Alright, now on the inside here, notice we can combine like terms if we just simplified a bit, and we're going to have something pretty simple in here. So that's a good approach. X squared times quantity x minus 2 times 2x plus 3x is going to be 5x, and then distributing the 3 we got a minus 6. That thing's factored, and we're ready to write our critical values. For solutions to that, x equals 0, x equals 2 from the factor x minus 2, and then for this last one, maybe you even want to set up the little equation, 5x minus 6 equals 0. That's going to happen when x is equal to 6/5. So those are our critical values. So that was a bunch of work. What are we trying to do? Part A, intervals of increasing and decreasing. So we needed those because we're trying to set up the intervals for which we are going to have increasing, decreasing intervals, and we need to know the borders of where potentially that increasing, decreasing nature of the function changes. So taking a look And another thing is we're looking at the domain of -1 to 3. And that's an important thing to highlight here, because if any of these critical values are not on the interval, -1 to 3, we don't care about them. We're going to set up our table now, where we have our intervals, and we want to work left to right. So starting at the endpoint -1, and we're going to go to our first critical value, which these happen to end up, well, not actually entirely in order. -1 to 0. Next thing is we're going to pick up at 0, and 6/5 is a little over 1, so that's the next critical value, working left to right. Then pick up at 6/5 and keep going to your next critical value, 2, which is still on the interval because it's less than 3. And then we'll finish this off by going all the way to the end, 2 to 3. So we're trying to get at the sign, meaning positive versus negative, of the first derivative, because that sign is going to tell us positive, it's increasing on the interval, negative, it's decreasing. So kind of a crafty way to do this. Your book doesn't do this, but it's kind of too bad because it's way easier and easier to think about. Just use a test value of x, plug it into the derivative, and we know from some of the things we've gone over so far that the character of that whole interval is going to be the same. The whole thing from -1 to 0 is either going to be increasing or decreasing because we're using the borders of the critical values, and that's where we could have a potential change in the sign of the derivative, is at those critical values, and that's based on stuff in 4.1. So anyway, pick something on the interval. It cannot be one of the endpoints, and that's why I specifically made these open intervals. So something that's between -1 and 0, try to pick something easy. Here we have to do like a decimal thing or a fraction. Unfortunately, I'm just going to go halfway between because that's not too bad, -1/2. Now 0 to 6/5, the really obvious choice is 1 because it's easy to plug into f prime. We'll do that in a minute. Again, you cannot pick the endpoints. That's where the character changes. It's at a critical value, so that's not, we already know there's something going on there. Either horizontal tangent line for all of them in this case, or the derivative doesn't exist. Okay, next one, 6/5 to 2, this is 1 1/5, so 1 1/2 is going to be okay, or 3/2, however you want to write it. And then from 2 to 3, I'm just going to go halfway between at 2.5, or it's a fraction 5/2. Now, f prime, reminder on that, okay, we're increasing, decreasing as our goal. And then we're done with our little table. So a lot of work in part 8, but then the other steps will get faster. So I'll write it up here that basically this equals 0 thing, that was the derivative. That factored form is a really nice form for doing this. And I'll show you this. You can play a little sign game. And then you don't actually have to calculate the value. You're welcome to actually calculate the value of f prime, but there's a little shortcut here. So notice that when we plug in -1/2 into the derivative in the factored form, we're going to get -1/2 squared. And then we're going to have x, oh, just kidding, not x, -1/2 minus 2 in parentheses, and then we're going to have 5 times -1/2. Cram it in here, minus 6. And then instead of calculating the value, just think about what its sign would be. And then we can multiply the signs to get the overall sign of f prime. So what we're going to get here is we got a negative squared. We got a positive value. Here we have a negative value for the second factor. This one I have to think a little bit harder, but we're going to get -5/2 minus 6. Okay, that's going to be negative. A positive times a negative is always a positive. Done. It's fast. don't have to do all those calculations or find the magnitude or the value part of the number, or not value part, the magnitude, the number part. Just need the sign. So the conclusion here is that it's increasing. If you want to make a little arrow going up left to right, that's fine. And we just do the rest of these entries in that style. So I'll write out the work for some of these. So 1 is easy because it's 1 squared, 1 minus 2, 5 minus 6. So we get a positive times a negative times a negative. So we get a positive again. And remember, that can happen. It doesn't always go up, down, up, down. Let's see if I can do some letters and make sense there. Okay, and then 3/2. I'm just going to write the result here. You can try that on your own time if you want. You should get a positive factor times a negative times a positive, which equals overall a negative. So it's decreasing on that interval. Last one, you should get a positive times a positive times a positive, which is a positive overall. So then it's increasing on that interval. So if you have a nice table, like my beautiful table here, where the intervals are the headings, then this is your answer to part A. I'll just write them out to show that. Increasing on -1 to 0, 0, 6/5, 2 to 3. So if this were live, someone might ask, well, can I just put -1 to 6/5 together? The answer is yes. Technically, I think your book does that. I don't really like it, but I won't take points off. Reason why is that x equals 0, technically the sign of the derivative is 0. It has no sign. So technically I like to leave the 0 out and not slam those together, because technically it's not a positive tangent line slope at 0. So I like to just leave them separate if they're in a row here. If you want to use union notation, that's cool. I'm just going to list them. Okay, moving on. Don't forget decreasing interval was from 6/5 to 2. And then we're done with part A. Part B, I'll just tell you what it says. It was up above. Was to find the local max and mins. Now, we've actually done all the hard work. All we need to do is use our table from above, and notice when we have increasing to increasing, at that critical value we do not have a local max or min. When we go from increasing to decreasing with the first derivative test, use a new color here. So right here, at x equals 6/5, we go from increasing to decreasing. And so the first derivative test is what we're going to use here. That tells us that we have a local max. Okay, anything else? We go from a transition from decreasing to increasing at x equals 2. Decreasing, increasing, it's a low spot, it's got to be a local min. So you don't really have to memorize the first derivative test, just be aware of it, but this should make sense on how you do this. You're really using the first derivative test, it's kind of a justification, but it makes sense, or should. So let's record it. Local max at x equals 6/5 Now technically we should find the y-coordinate when it just asks for the local max, and not just the x for which we have a local max. A lot of times I'll state the x just because I want to save work for you, some work on you. But for this one I should probably just show you the full-blown thing. So the y-coordinate is defined by taking not the derivative, but the original function evaluated at 6/5. So that actually was way less complicated than the derivative, so it's not too bad. 6/5 cubed, 6/5 minus 2, that quantity squared. Alright, so what you get here, I'm just going to write it approximately, actually, is 1.10592. So sometimes, again, this is just going to be fine. Oops, I should circle the whole thing. Or I'll just put down here, you could report again as a point. The other one, local min, with an x equals 2, so let's find the y-coordinate for that. When we plug in 2, we're going to have 2 cubed, 2 minus 2 squared. That's easy. 0. So when we report this, local min at x equals 2, so time is going to be fine, but you would plug in to get the y in the original function to 0. We're done with part B. One last part. I'm having fun changing colors, so I'm going to keep doing that. Part C. Alrighty. We're supposed to find the absolute maximins. Well, we've actually done a lot of the work. Excuse me. So we have a closed interval here. And so we have, on the interval, we have our local mins and max. We can't have local mins and max at endpoints, but we can have absolute max and mins at the ends of the interval. So let's check the endpoints. It's a continuous function on a closed interval, so by the extreme value theorem in 4.1 we are basically just need to check what the y-coordinates are and see if they're higher or lower than what we obtained for the max and mins, the local max and mins on the interval. So f of -1, because our endpoint was -1, you plug in and you get -9. F of 3, the right endpoint, plug in and you should get 27. So I'm not showing the work there, but already kind of showed how to plug in. Okay, so now we got to compare with what we had up here, and it's on the same page, or you could look at the table. So we had a local max at x equals 6/5, and the y-coordinate that went with that was 1. We're looking at that versus -9 versus 27 versus 0. So let's go with the lowest one first, and that will be the absolute minimum. So because this value of -9 for y-coordinate is the lowest, we have an absolute min at x equals -1, or the point would be -1, -9. The absolute max, we guarantee you have at least one, is going to be at the high point. So we have about 1.1 whatever, 27 versus 0. So that's going to be also at an endpoint, at the right endpoint. And so that's at x equals 3. or reported as a point, it would be 327. Okay, we are finally done with that problem. However, I do want to show you the graph of this. This is what we're going to be doing a little bit. Switch to a plum color here. So we're not graphing yet, but we're actually going to start graphing in this unit, so this is really soon. It's like the next thing we're going to do. So what you can do is you can pull everything together, like the increasing, decreasing intervals. These points are going to be critical. You plot the points because obviously your graph has to go through those points. And this is not going to be great graph here. Let me get some scales on here because we are going all the way up to 27. And so this goes down to negative 10, 10, 30, etc. And then we're going to make this kind of really stretched out here to show what's going on. So we have a point at negative 1, 9. It's an increasing function. It turns out the curvature looks like that, which we haven't gotten to yet. And then we have a relative max at 6/5 and about 1.1. Wow, I'm not giving myself much room to do this. Alright, this is going to be... Sorry dudes, I need to start this over because I can't even draw that. I'm going to use this whole space allotted to be able to show what I can do here. Alright, try again. 10, 20, 30, 10 down here, negative 1, 1, 2, 3. I can do it. 10. Okay, negative 1, let's see here, negative 1, let me go back. Oh, it's negative 9, yeah. I think I said 9 on the last one. Sorry about that. Okay, negative 1, label that sucker. Negative 1, negative 9. Down there. That was an absolute min. We have a critical value here. You cannot get the curvature at this point very well, but believe me, it looks like that. We get a maximum at about 1.1, or 6/5, 1.1. So it's still kind of hard to draw, but we'll put that point there. And the curvature is going to be sort of, oh, I can't do that. Try again. Wow, that's actually pretty darn good. Kind of like that. And then actually goes back down to 2. Junk. I shouldn't have stretched out my x-axis so much. I made this really hard on myself. Okay, that's 2, 0. And at 3, it spikes up all the way to 27. Ooh, okay, 327. I can draw that. And the curvature you can't get right now, but it kind of looks like that. Alright, you are going to have to do this pretty soon. So, that's it.